Hello and welcome to The Chemist. I am Shelby Watson, your teacher person for this. Um, I will be teaching you about hybridization today. I am, I would say, pretty qualified to teach about hybridization. I'm a PhD candidate. I'm currently getting my PhD um, in the recycling of polymers and kind of fixing the recycling system. So that's what I'm doing. So let's get into this. That was a gross noise, wasn't it? Okay, so let's start our screen and we'll get into this. Okay, so I written down a few notes before we got started. Basically, I'm going to use carbon as an example. I think it's a really good example to start off with. Carbon is, I wrote the 12th element. That was wrong. Carbon is think about it, guess, it's the 6th element. Its molar mass is 12, around 12, in regular carbon, it would have like 12 protons, 6 protons, 6 neutrons. That's how you get the 12, but it's going to be like 12 point something something because there's different types of isotopes of carbon. There's carbon-13, which is used in NMR, and so that's why the decimal points is like the average of all that. So these are some basic examples. So if we're thinking about like a periodic table, okay, la 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 la, lovely, horrific drawing. Let's say that, this is hydrogen, got helium, and over here is carbon. This first row is, I would say, full. That's your full inner ring, so you can't access it for bonding. So if I was to write out carbon's electrons, it would be S1s2, 2s2, which is, again, right here. And then it would be 2p2, because we're only going over 2 to right here where carbon is. And so I would call this your core electrons because these don't interact at all with bonding. These here are your valence electrons. And so if I was going to draw those in like a molecular orbital diagram sort of way, that, or all of this would be at 1s, 2s, 2p. You draw it like that. Again, these are the only electrons that you're using for bonding. And you may be thinking, I already know this, why do I need to go over this? This basis is really important to understand before we can get into why we have to hybridize things. So if we're looking at this, like carbon, the way I like to think about it is that everything that's noble gas doesn't want any bonds. Their shell is full. You can think about fluorine is 1 away from the noble gases. It wants 1 bond. Oxygen is 2 away from noble gases. It wants 2 bonds, like water. Carbon is 4 away from noble gases. So it wants 4 bonds. So if we look at how it's set up here right now, to have a covalent bond, there has to be a sharing of electrons. So
covalent bond share electrons. And I'm just going to use this as an example, like two different hydrogens, you know, they both have electrons. They'd come together like this to share those electrons, okay? So there's only two spots here. In the way things are set up right now, carbon can only make two bonds. So that's where we have to hybridize this, because carbon would prefer to look like this. So if carbon needs 4 bonds, that means we need 4 half-filled orbitals to make covalent bonds. So we need 4 half-filled orbitals to make 4 covalent bonds. And so we're going to change 2s to p that looks like this into this. And you can think about it like we have p's over here and we have an s. If you want to count it up, you can think, okay, I have 1s plus 3 p's. So right now, that's sp3. Altogether, that's 4 orbitals. That's 4 orbitals to make covalent bonds, to make single bonds. So, sp3, let's dive into a little bit more what it means. sp3 means that we have 1 s orbital and 3 p orbitals, 4 in total, to make single bonds, okay, that's important, or lone pairs, okay, single bonds or lone pairs. So some examples that maybe you wouldn't have thought of otherwise. We have carbon here. Let's just put hydrogens on those because, you know, why not? These bonds are going to be sp3 because they're all single bonds. They're single bonds, they're sp3s, there's no double bonds in the mix. That's what we're doing. If we look over here, oxygen and 2 hydrogens with water, you may be thinking, okay, that's not sp3, there's not 4 bonds. Okay, but the difference is that we have to complete the octet rule. So therefore, that's what these 3 dots means. There's no need for a double bond because oxygen wants to have 8 electrons and oxygen already has 6. Let's write this out so this can make more sense. Oxygen has 6 valence electrons. Hydrogen has 1. I don't know why. So we have 2 of those. Overall, that's 8. Okay. And so here and here, those aren't double bonds. I'm just highlighting. So let me do it like this. Here and here, that's 4 electrons, minus 4 electrons. We still have 4 more. Where are those going to go? They're not going to go on the hydrogens. Hydrogens don't want more than 2 electrons. So they're going to go over here. And if we're thinking about this, over here I said sp3 means that we have 4 in total single bonds or lone pairs. So we have 2 single bonds and 2 lone pairs, which in total makes 4 orbitals, 4 spaces. So let's talk more about the octet rule real fast. So, octet rule, okay? Noble gases already have 8 electrons. They're full. They don't need anything else. Every other atom wants to be full like a noble gas, and that's why they try to make that octet. Other atoms want to be full like noble gases. Okay, so we have carbon. It wants 4 bonds to get those 8 electrons. Nitrogen, it's 3 elements away from noble gases. It only wants 3 bonds because it has enough space to have a lone pair where it only needs 3 bonds. These are very much patterns you can get. So 3 bonds and 1 lone pair is equal to 8 electrons for nitrogen. Oxygen, like I said, it's 2 away from the noble gas. It only needs 2 bonds to complete that octet rule. So 2 bonds and then 2 lone pairs. So it only needs 2 bonds. Or, and leading into the next part, oxygen could be, let me move this. Oxygen could be double bonded to something. And carbon could have those 4 bonds, have to have that octet, but one of those bonds, let's say it's this one, is a double bond. So double bond to, I don't like how I wrote that, bond to complete octet. Once you get past the first row in the periodic table, not including like hydrogen and helium, but after that, and you have like your d orbitals and stuff, you can break that octet. You can have more than the 8. Yeah, I don't think you should have less, but you can have more once you're in the d orbitals and stuff. So we have a double bond over here. What is that? That's sp2. sp2 means 1s and 2 p orbitals are being used for single bonds or lone pairs. Okay. Again, single bonds or lone pairs. That's 3 in total. So we have 1s plus 2p's. That's how we get sp2 the one for the S is like imaginary. There's 3 in total that are being used. So that leaves 1 p orbital, that B looks weird, left to make a double bond. A lot like the one that we just drew. So if we redraw the one we just drew up there, and we went to analyze this, well, it wouldn't be sp3 because we don't have 3 p's. We only have 2 p's, so it has to be sp2, because if we're looking at it, this is an S, these 2 are p's, and then we have this p over here by itself to double bond. So there's only 3 bonds there to make covalent bonds. So this is sp2, this is sp2, and let's say that, looking at double bonds, okay? Let's say that this is the double bond, and this is also sp2, because you need a single bond first as like your foundation before you can build on top of that and give it like a double bond, a triple bond. You have to have a single bond there first, okay? So then this right here is your double bond, your p orbital. Okay? Hopefully that makes sense. And so this is where it's going to get a little bit of complicated, because I'm going to talk about, like what that looks like. Well, I'll go over SP and then I'll get into some more complicated stuff. So if we take, let's pick another color. If we take another p orbital, put it over there, then we have an S, a P, 2 P's over here, double bond. So we could have 2 double bonds or triple bond. We keep them all up in the same spot. That's SP, which means there's 1 S and 1 P, 2 in total, used for single bonds or lone pairs. That, hello bird, that leaves 2 p orbitals to double bond. So again, let's highlight this. Probably not a great color to highlight with. So let's go over an example. Let's say that we have HCN, okay? No, I think a good starting question is, if these are my pi's, okay? These are my pi bonds, or my p orbitals. I think I gave it away. What would you call this? It looks kind of like a sandwich at this point. You have R, X, these are just random things. This is a single bond. This is what a double bond looks like. And this is what a triple bond looks like. And as you're going down this little thing that I made, the bonds are getting stronger, and the bonds are getting shorter. So the bonds are getting shorter. That's creating a larger overlap between these two atoms. And because there's a larger overlap, we have Z effective in play. And so the electron cloud around these atoms are now, they can interact with, because the closer the electron cloud of one atom is getting to the other atom, it's getting closer to the nucleus, to those positive charges. And once those negative charges get so close to positive charges, it's going to be a very strong interaction. You're not going to want to break away from each other. So that's kind of how that works. So back to SP. Yeah, I drew that up there. So there's only two purples. Oh, sorry. There's only two purples. So this is SP. This one is SP. You can count it. The smallest it can be is S. Is hybridization, so it's not just going to be S. And so then these are P. I don't think I use the same color, but these are P. And so let's go over like what S and P look like, and like sigma bonding and things like that. So let's pick a new color, dark green. This is an S orbital, okay? This is a P orbital. So the shading is just a type of charge. It doesn't matter if it's positive, it's negative, whatever. And the important thing is to note is that these two don't have the same charge. Okay, that's important. So if I was to draw a molecular orbital diagram, I'm just going to draw one. Let's say we have F over here. We have F over here. Oh, you know, just for an example. So we have 2S, 2S, 1, 2, 3, 1, 2, 3. This is 2P, 2P. Electrons, we're filling in. Now, if you have questions, the way I'm filling this in, so I'm just filling in these separately first. Like I'm just filling in how many valence electrons I have for fluorine, like no big deal, like that's what that is, okay? So then what I'm doing is, because essentially we're looking into the theory, or proving the theory of bonding and how stable a bond is. That's what we're doing here. So this is just the proof behind the theory, okay? Then what I would do is I would just fill in. So I have, let's say, I need 2 electrons in the bottom. All right, fill those in. I need 2 electrons in the top. Okay, fill those in. I need an electron from the bottom. Okay, cool, fill that in. I need an, oh goodness, wrong color. I need an electron to fill in right here. I need another electron to go over here. And as you can see, like at this time, I'm filling it in, you know, making sure everything like goes in to as best as it can. And it may not get to the top, and that's fine. That's just depends on how many electrons are there, you know? So, sweet, we filled this in with the right amount of electrons. So then we have to label this. So this is sigma, this is sigma, this is sigma, and this is sigma. Sigma is when your bonding is head-on. It has the best overlap that way. And this right here is also sigma because it will have the best overlap. You can also think about it like this. If I draw a line through these and I spin it around on this axis, will the charge change as I'm spinning it? No. These charges don't, or let's say the charge signs don't change. Okay. So these are pi. And you can guess pi would be like this. The interactions are side-to-side interactions, side-to-side bonding. That's how they would bond. And if I drew a line through this and I turned it, as one side goes down, the other side comes up, the charge sign changes. Okay? So then what we have to do is we have to say whether it's bonding or anti-bonding. Okay? This is anti-bonding. This is anti-bonding. This is anti-bonding. What does anti-bonding mean? More importantly, if it doesn't have a star, so let me do it like this. No star means that it's bonding energy, okay? Has a star means that it is anti-bonding or dissociation energy. So I was going to draw something that was like, oh, you know, this is bonding. They're the same sign. This is anti-bonding. They're different signs. So hopefully that helps make sense. So let's look at it. This is anti-bonding. This is anti-bonding. This is anti-bonding. This is bonding. This is bonding. This is bonding. Okay, so if we're looking at you're asked the question, what's the bond order? Well, to put it simply, you can put it as half of bonding electrons minus half of anti-bonding electrons. Okay, so in this case, if you look at it, it would, let's put it in gray since everything else is in gray. I'll write it up here. The bonding order would be, let's see, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 1/2 of 8 minus anti-bonding. Let's see how many we have. 1, 2, 3, 4, 5, 6. 1/2 of 6. You can simplify that to 4 minus 3, and that's 1. That's 1. So this compound of F2 has only one bond. You can also write, let's put over F2 has a single bond. If it's a double or triple bond, it would be stronger. And this is a way for you to look at strength of a compound, because you have this anti-bonding energy up here. It's not as strong as it would be if it ended down here, you know, like there is some dissociation energy. It's why it's only a single bond. It's not as strong as it would be as a triple or double bond. And that is really everything that I have for you guys today. I hope that this helped you understand, nope, stop.
Anyways, I hope that this video helped you understand hybridization and kind of how the previous rules that you might have learned come into play for something like this. And comment down below things you would want me to cover in the future. Comment below any questions you have, and I can maybe answer those in a different video. In the description, I will be putting my email, so you can email me questions, and just overall like contact information and things like that. And I will see you guys in the next one. Bye!